Hello students, so today we are going to move into Newton's laws of motion, right? So let us start laws of motion. This is also called dynamics. So now we are in the dynamics or laws of motion, okay? So as far as JEE Advanced is concerned, considered, we are not going to more detail in that. We are focusing on mainly on JEE Main. So we will not be also going into much theories, right? Because your exam is next month, right? Starting from 4 to 15th, right? So you need to focus on all the hot topics so that you can work out problems easily, right? So let's start with Newton's first laws. Without wasting much time, we will start Newton's first law. So what is Newton's first law? Okay, so Newton's first law says that all those statements all of you know, right? The body at rest remains at rest, body in motion will continue to maintain motion unless some external force acts on it, right? All those things are there. We are not going to write all those, but we'll write here like if net force is 0, or you may say if acceleration, and it's a vector, so we can write in terms of vector, acceleration is 0, then velocity can be 0 or velocity can be constant, right? So if this is 0 velocity, that is called rest, and if this is motion, this is called uniform motion, right? So if there is no external force or no net force acting on the bodies, so its acceleration will be constant. Acceleration constant means velocity is constant, but that constant can also be 0, right? That's a different state of motion. So this is, a rest, and this is uniform motion. Mathematically, this is the description of Newton's first law, right? And Newton's laws of motion we study from inertial frame, right? What is inertial frame? Inertial frame is, frame is of reference with the coordinate system, but inertial frame is the frame which is at rest, or if it is having 0 acceleration, and non-inertial frame means which is under acceleration. So of course these are little theories, but as far as JEE Main is concerned, questions are not coming more into theory, or maybe some reasoning based question will come, that we will see. Okay, this is what is Newton's first law. So from here, this is also known as law of inertia, right? It is known as law of inertia. Why? Because if a body is moving with a motion, of course rest means, okay, we can understand it is at rest, but how can you say that if a body is motion, right? Let's say if it is moving with a constant velocity is constant. So if velocity is constant, there must have been some force on it, that's why it is moving. But no, actually there is no net force. There may be individual forces acting, but net force is equal to 0. Okay, this is what we have to understand. The body is in equilibrium or balanced. So previously people were not knowing about the cause of motion. What is the cause of motion? So cause of motion can be, generally it is force, like when you apply some force, then only body moves, right? But if a body is already in motion, we don't have to apply any force. It will maintain its state of motion, right? So that is because of inertia of motion. So inertia is the inherent property due to which a body maintains its state of rest or motion. So what is inertia? Inertia is inherent property due to which a body maintains its state of rest or uniform motion, right? So if your body is at rest, it will remain rest because of inertia of rest. If your body is moving with a uniform motion, it will maintain that because of inertia of motion. Okay. So only if you want to change the state of motion of the body, then only there will be resultant force which you have to apply on your body. Otherwise, you don't need any force, right? Okay, so first this law gives us idea about inertia, and inertia is basically proportional to mass. More mass means more inertia. Okay, more mass means more inertia. More mass means more inertia. Okay. Okay, now let us go to the next, Newton's second law. Newton's second law. Newton's second law. What does Newton's second law? This is the major law which we have to see in this chapter. A lot of applications are there. Okay, so Newton's second law gives the method to calculate the net force. So suppose if there is a body, right? Let's say there is a body and its momentum is changing. Momentum is mass into velocity, right? So if this body's momentum is changing, then there must be a net force on it. Because of the net force, momentum changes. Okay, suppose you are applying some force on this body. Okay, so its momentum is changing. So suppose you are applying some force on this. This is the only force acting, or you can say this is the net force. There may be many forces acting. This is the sum of all the force. Okay, so the resultant force, the net force acting on the body, is equal to rate of change of momentum of the body, dp by dt. Now momentum is mass into velocity, so you may write this as mass into velocity vector, right, by dt. Now we can take two cases, case 1 and take case 2, two cases. We try to understand through these two cases how to calculate the net force. So first case, we keep the mass of the body as constant and velocity is not constant. Velocity is not constant. Velocity is changing. So net force equation from here will be, mass will come out and this is dv by dt. dv by dt is acceleration, so this is mass into acceleration. Okay, that's the first, and this is the most general form where we are using this equation. Net force is mass into acceleration. Second case, you take mass is not constant but velocity is constant. Let us take that. So in that case, net force will be equal to, this time velocity will come out and it will be dm by dt out. Right, so this is the another form of Newton's second law. This we use in cases where the mass of a body can change. Right, we will see some cases. Right, so this is Newton's second law. Okay, then let's go to Newton's third law, and again we'll come back to applications of Newton's second law. Okay, Newton's third law. So Newton's third law says that whenever two bodies interact, let us say that there is a body, right? There is a body. This is a big body. Okay, and this body is interacting with another body. Let's say this is another body. Two bodies are going to interact. Okay, so this will apply some force. This will apply some force. There is an interaction between. The interaction may be contact or non-contact. That's different. But these two bodies, first body and second body, they are interacting. Okay, bodies 1 and 2 are interacting. Right, they are interacting. Now here we should know one thing, that this, let's say this is the force on 1 and this is the force on 2. Okay, so this is pair of forces. One is called action, another is called reaction. So action which is F1, and reaction which is F2. Action and reaction are pair of forces which exist together. That means if there is action, there will be reaction. Okay, and action and reaction are equal and opposite, that you can write in terms of vector. F1 is equal to minus F2. Okay, so their magnitudes are same, but they are opposite directions is opposite. Also important thing to note that action and reaction forces act on two different bodies. They are not acting on the same bodies. You can note this. There are different bodies on which they are acting. So let's say F1 is acting on first body, F2 is acting on second body, right? This is Newton's third law of motion. So having done this, we'll revisit the applications now, and thoroughly application will be based on Newton's second law of motion. Okay, so let us see the applications of Newton's law of motion, Newton's laws of motion. So in order to apply that formula, in most of the cases we are going to see the application of net force is equal to mass into acceleration. This is the major application that we are going to see, right? So how do we apply? So there are three steps to follow. Step 1 will be to draw a free body diagram. Free body diagram. Okay. Step 2 will be to calculate net force. Calculate net force by vector addition or resolution. And the third one is to use net force is equal to mass into acceleration. Okay, so these are the three fundamental steps that we should be able to do it. So let's go into detail about these three fundamental steps. First step is free body diagram. So we need to look at the free body diagram, how to draw the free body diagram. Okay, and during that itself we will see the 4 to 5 fundamental forces, because without knowing the forces, how will you draw the free body diagram? Okay, so let us also look at the forces, types of forces. So basically we will see the different forces. First force is gravitational force. Gravitational force, which is also called weight. Second will be tension force. Third, normal contact force. Fourth, friction force. Fifth, spring force. Okay, these are the 5 forces that we should know. Then we can work out questions on Newton's laws of motion very efficiently. Okay, we need to understand this. So they are easy and quickly we will be doing, right? So let's start with. Then after that again we'll come to those fundamental steps of Newton's laws, right? These steps again will come back. So let's start gravitation. So gravitational force or weight, here it is the gravitational pull on any object due to Earth, right? So suppose this is a big object or any object. every object is getting attracted towards Earth. Let's say that this is the Earth, toward the center of the Earth, right? Earth is pulling everything by this force, which you may also write W as the weight. So this W is equal to M into G. Okay, and G value you know 9.8, right? M is the mass. So very simple. That's the attractive force, and it's going down towards the center of the Earth. That's how we have to know this. Okay, and there are some unit, like sometimes unit confusion may happen, like what is 1 kgf? 1 kgf is the weight of 1 kg. So M into G, 9.8. So this is basically 9.8 Newton, 1 kgf. Okay, similarly 1 gram force, 1 gf. 1 gf will be weight of 1 gram. 1 gram means 1 by 1000, right? And G is 9.8. So this is 9.8 into 10 power minus 3 Newton. Okay, this is gravitation, right? Next, let's go to the tension force. Tension force. What is tension force? Tension force is also it's a physical interaction between two objects, right? So let us say that there is a string, and from this string an object is hanging, right? Let's say that this is an object which is hanging, the block is hanging, right? So now there will be a upward force on this, right? Upward force on this object, because this string is trying to pull this object and gravity is trying to attract it downwards. So if this object is balanced, so we will say T is equal to mg, right? T is the tension force. So tension force is developed in the string, and a string pulls all those objects which are attached to it. So even the ceiling is being pulled by, you know, this wire, and the tension force is acting downward if you draw the free body diagram of forces on this ceiling, right? So tension is like this, that it is always moving away from the body on which you want to show the tension. And tensions are developed in strings, wires, ropes, etc. Okay, and it is always a pulling force, and it acts along the string, along the string. Okay, so tension is supporting. But suppose also important point to note that if this string is ideal, then tension will be same. Tension is same throughout the string, which string? Ideal string. But tension will be not same throughout the string in case of a real string, because the string will have also its own weight. So and also you should know what is the tension. Suppose this is a body hanging. So suppose if you want to find tension at this point, okay, this is point P. So tension at this point is weight of the portions below this point. Okay, you have to note this, weight of this portion below, that means this whole weight. So weight below that point is the tension acting at that point. Tension at the top is the total weight of the string plus this block, right? So maximum tension will be at the top, minimum tension will be at the bottom of the string, right? So tension will vary from minimum to maximum as you go up in the string. Okay, that's tension force. Then if you draw the pulley, generally you will see the questions on pulley. So pulley is connected like this by string, and there are two blocks like this, okay, 1 and 2. So tension on each of these you have to show upward like this, and because this string is ideal, we have to show the same tension acting upward. And gravity, of course, you can draw mg. So this is m1g, this is m2g, like that you have to draw. Okay, this is tension force. Then let us see the normal contact force. Normal contact force. Normal contact force. What is normal contact force? Suppose there is a block, okay, and this block is resting or it is in touch with this ground, okay. So there will be interaction between this body, right, and this ground. So the normal force that will be acting on this first block will be in this direction. It is normal means it is perpendicular 90 degree to the surface, contact surface, and it is acting on the body upward direction, or it is coming out of that plane. I mean to say it is coming out means it is going up, acting on the body away from the second body, right, away from the second body, right. So you may show that it is like this, that's the normal force, but why we are representing, because at the contact surface we have to show this is the contact surface, right. So at that contact surface we should show this. Okay, this is how we can show the normal contact force acting. And suppose there is no contact force, that means contact is lost. So normal is equal to 0 means contact is lost. Contact is lost. The body may separate also. Okay, right? This is what is normal. Similarly, if suppose there is a wall, let us say, and there is a body like this. So here the contact force that should act on the body is like this. So you need to apply also some force. Suppose you are pushing this like this direction, then the normal will be balancing this, right. So normal is equal to like this. So normal force will be equal to the interaction. For example, here if you see on other forces, mg is also acting downward. So mg will balance normal if vertically it is balanced, right. So here normal will be equal to mg. But in some cases, like on inclined plane, when you see here, mg is acting downward, right, mg is acting downward, and normal to this surface, contact surface, will be acting like this, right. So normal will not be balancing mg here. Here you need to resolve, but the resolution will depend, like what is the condition, whether you are keeping it just like this, or the whole system is moving in some other direction. So resolution will discuss which forces to resolve when and why, that we will discuss separately, but this is how the forces will act. And also you should note that normal will make the same angle theta with the vertical which the inclined plane makes with the horizontal. Okay, normal makes same angle theta with the vertical. Okay, so here normal will not be equal to mg. Suppose if you have just left this body on the inclined plane, then it will only slide down this direction. So we should resolve forces along this direction and this direction. So in one direction it will be this mg cos theta, right. In this direction force will be mg sin theta. Why? Because body is having net acceleration in this direction. That's why we should resolve along the plane and perpendicular to plane, right. So here normal will balance mg cos theta, and resultant or unbalanced force, net force, will remain mg sin theta. Okay, then you can write this as mass into acceleration, therefore you will get acceleration is equal to g sin theta, right. So if you just leave this body will go down with the acceleration equal to g sin theta. Okay, so this is about normal. Then let us take about friction force. So friction force. So first of all, friction acts due to roughness of surface. Okay, it acts due to surface roughness. Surface roughness. And second point is that it acts when body has a tendency to slide over other. Okay, it acts when there is a tendency of relative motion. So suppose for example if you take one object like this, right, and let's say this is on ground. The ground is rough, right? The ground is rough. So what will happen? Let us say you apply a force in this direction, so that if there is no friction, let us say the surface is smooth, then obviously this body will slide in the right direction. But because there is a tendency for the body to slide, friction will act on this body at the contact surface and it will act in this direction. Okay, friction will act in this direction. So this is the force I am showing on the first body, right? Suppose this is the ground, which is body number 2. If we have to show forces on the ground also, we can show. On the ground, the friction will act in this direction, right? Because friction is also a contact force and it forms action and reaction pair. So the second body is giving this friction force on the first body in the upward direction. Okay, so you can understand this more clearly. Let us say only I am showing the upper body. So on the lower body, second body, okay, the friction is going to act like this. So actually this body is in contact with the ground, okay, and this is the surface. This is the first body, this is second body, and you are applying a force. This is applied force. So now you can see on the first body friction is acting backward, second body on the ground friction is acting forward, like this. Okay, this is the real free body diagram. But other forces I have not drawn. But other forces, if you want to draw, you can draw here mg acting on this, and normal interaction force on the surface, right, will be acting like this. Same normal force should act like this. Here you should not think that mg is acting on the second body. This is the common mistake students do, right? Mg is the weight acting on that body whose mass is m, right? Normal is acting because of interaction between the two surfaces. Okay, you should know the normal which is acting, that is n is common to both the bodies. The first body normal is acting upward and the second body normal is acting downward. Okay, so this is how friction is acting, and here we can note the formula for friction and how friction works. Briefly we will just discuss about friction. So let us say there is a block, okay, and this is a rough surface, and you are applying a force F. So on this first body we are studying, friction will act in this direction, right? So let us say you apply this force, keep on increasing, but body doesn't move. So this friction is called static friction, and we can draw the graph of this friction versus the applied force. Okay, so this F will be equal to capital F up to when the body is at rest. Okay, rest. So we keep on applying, and this force is equal to that. Okay, up to when body is at rest. So but if you apply very large force, then friction cannot go. So friction is going to increase, and if the applied force become greater than or let's say it becomes equal to maximum friction, maximum static friction. Here this is also static, okay, static only because the body is not moving. So this is the first case. Second case, third case, you can take F is greater than maximum static. So in that case the friction that will act is the kinetic friction. Okay, so how this graph will look like? First of all, this graph will look like at an angle of 45 degree, because whatever force you apply, it will be balanced by this. So both F and F are equal. So under this condition, this is static condition. Okay, this is the static condition. There will be a maximum value of the static friction. This is F maximum static. Now after that, if you increase more than that, the graph will go little bit down, it will go, and after that it is going to be constant. Okay, so this graph which is coming the lower point, okay, this one, This one is kinetic friction. Kinetic friction is a constant value. So after this is static region, this is kinetic region. Okay, kinetic or dynamic regions. Kinetic friction, this is static friction. Okay, so what is the law of friction? Here we should know we have the formula for maximum static friction. Okay, maximum static friction. Maximum static friction is mu static into normal. Okay, and similarly we have kinetic friction. Kinetic friction is mu kinetic into normal. Normal is the normal contact force between the body, right? So these two formulas we should know, and also it is important to know that mu static is greater than mu kinetic. That's why the value of maximum static is greater than the kinetic friction. Okay, greater than kinetic friction. Also, one very key idea to note that friction will always be less than or equal to maximum static friction. This condition we can apply in many portions, right? Okay, because that's the maximum value of friction, that is the maximum static friction, right? This value of friction. Okay, so this is about friction, and this is the law of friction, laws of friction. This is how friction acts. Okay, right. So this will be useful. Then last is the spring force. Let us take about the spring force. Spring force. Okay, so how many we have taken? We have taken about no, I think this is the fifth one. Spring force is the last one, right? Fifth. How does a spring force act? So suppose that there is a spring, this is a wall and a spring is connected, and there is a block. Okay, and let's say this is the natural length of the spring. Now suppose, and this is the ground, let us say. Suppose you stretch this, or you pull it this side, you pull this, and then what will happen? You know, this will come, it will stretch like this, right? It will stretch, and this will come here. Now what happens is that, let us say that you are going to release this. This is the block, right? This is the block, and now this block, let us say you are going to release it. So if you release from here, you can release. So what will happen? As soon as you trying to stretch it, there is a force developed in this string, and that string is connected with this spring is connected with this. So there is a spring force developed, Fs the spring force. So the formula for spring force is minus k into x. What is x? X is the elongation, stretching in the spring or compression from the mean position. So x is displacement from the mean position, from the mean or equilibrium position. So if you have stretched this spring towards the right side, force will be towards left side. And if you have compressed it, let us say, if you have compressed this like this, and this is the block. Okay, so let's say if you have compressed it, so from the equilibrium position you have compressed it by some distance, let us say x, right? So force is going to act on this in this direction. That spring force will be minus kx. Okay, minus because it is opposite of the displacement, and x is k is a spring constant. K is called spring constant. Okay, so this k will depend on what factor? This k depends on two factors. Depends on first nature of spring. Okay, and second, it is k is inversely proportional to length for a given material, or a given spring. Okay, suppose this is a spring made up of some fiber. So if you take the same spring 2 times, 3 times length, so K will decrease, right? So K is inversely proportional to the length of the spring for a given string. Okay, these things we should know. So these are the important forces. Then gradually we will discuss Newton law applications in the next videos. Okay, thank you for your attention.